some well, it's going to be decrement, obviously, so d nu is going to be negative. Well, the number density is denoted usually as n. It's how many particles are per cubic centimeter. But then each of them has a cross-section area, which will be more or less comparable to its actually geometric cross-section. So then you just simply add up all the area that those photons are likely to encounter, and here it is. So now what happens? There'll be a fraction of radiation that's absorbed that will be proportional to the fraction of the area that's been blocked by absorbers, like dust grains. And you can express it in the following way, that change in intensity divided by intensity itself, so it's a relative fraction, it's going to be negative because light is being removed, not added. It's times some cross-section, that's combination of the density and so on, and the path length. The longer the column, more likely you are to encounter. Right? And so this is a very simple differential equation that is trivial to integrate. So it's dx over x, the integral is ln x, and then the other one is just integral of x dx. And so that there will be just integral of dx, and so there will be just the path length. Now I'll take exponential of both sides, and I have that the ratio, because this was logarithm, right? The ratio of the intensity at the end to the intensity at the beginning is proportional to exponential function with a negative exponent that's linearly proportional to the length. So as radiation goes through some absorbing medium, its intensity declines exponentially. And this is why dust clouds are so effective in hiding parts of the Milky Way behind us. Now, this exact same treatment would apply to, say, plasma inside stars, except this would be a whole different set of wavelengths and so on. So astronomers like to express this in following way. This is so-called extinction curve, which gives you, well, optical depth, which is how many e-folding lengths of extinction do you look through as a function of wave number, 1 over wavelength. And so the infrared is on the left, ultraviolet's on the right. And you can see that the infrared, well, those photons tend to kind of go through, no problem. As you go to shorter wavelengths, the dust is more effective in absorbing. And if it wasn't for this little bump that's due to silicate dust grains, it would be more or less linear proportion of this logarithmic decrement. Wait. Okay. Questions about the dust? Yes, please.
How would you capture the dust to study it?
I'm sorry, what?
How would you capture the dust to study it?
How do we know that those are silicate grains?
Yeah, how would you capture and study dust?
Well, we can't capture any. Spacecraft will have to go far away, so we have to use what we know about atomic and molecular spectroscopy and infer from what we see in absorption and emission spectra what are the chemical elements and molecules that are involved. And people can model this. You can start with a reasonable guess because we know what kind of elements tend to be preferentially cooked up in stars. And silicon is one of them, oxygen definitely. And so you can do models and find out that essentially interstellar quartz, it tends to be the one of the components. Anybody else? Yes, please.
So all of the pictures that we're seeing are kind of developed through...
Well, imaging through different filters. Spectroscopy will be much higher resolution. But if you take picture in 3 filters, like your cell phone camera, which has little red, green, and blue filters in front of adjacent pixels, then you can combine them into a full color picture.
And since the Earth is in the middle of the Milky Way, all the pictures are being taken from satellites orbiting the Earth,
No,
correct?
well, some pictures, obviously, we can take from Milky Way. You can see the Milky Way at night on a good site, right? So whatever wavelengths go through Earth's atmosphere, we can certainly do from the surface. But for example, far infrared doesn't go so well through Earth's atmosphere, and that had to be done with satellites. So it would be the case with X-rays, for example. But H-alpha emission, hydrogen alpha, that's a 65, 63 angstroms. That is easily visible through Earth's atmosphere. Okay, so interstellar dust. Who thinks that A is correct? How about B? Okay. How about C? It's good to know that approximately 5% of you are paying attention. How about D? And how about E? Okay. B is correct, C is correct, and D is correct. The sizes are more like 0.1 millimeter or smaller. And we just went through a long discussion why objects of a given size would actually absorb or reflect wavelengths that are smaller than their size. Now let's get into some more interesting stuff. Star formation. Talk about false color pictures. This is a beautiful false color image of the Eta Carinae Nebula. There's a lot of star formation going on. And you can recognize that there is some blue light, so that's some young stars scattering light of the dust clouds. There are pretty obvious dust clouds too. And there is some reddish glow to it, which is coming again from ionized gas. But what's relevant for star formation is the cold part of the interstellar medium, the part that can condense. And this is a picture from Herschel satellite that is mapping particular giant molecular cloud in several different wavelengths. And again, you can see that these clouds are nothing like spherical, and they have this knobby structure. So all the dense spots are the densest clouds is where stars can form. So the way we study them is through millimeter wavelengths, mostly from planet Earth, and that's usually done with interferometers of telescopes, which have receivers in the range of wavelengths of the order of 1 to a few millimeters. Caltech, jointly with a few other universities, is operating one of these arrays in California. It's called CARMA for California Array for Millimeter Astronomy. And the world's biggest is now operating in Chile. That's Atacama Large Millimeter Array. There are others too. Interferometry is the popular way of doing radio astronomy because it allows you to resolve things with separations of antennae, not limited by the resolution of any individual antenna. And the typical molecules that we see out there are, first of all, molecular hydrogen, atomic hydrogen being the most common thing. Molecular hydrogen is not likely to lag behind. But then there'll be carbon monoxide, not dioxide, monoxide, and ammonia, and a whole bunch of other stuff, including some very, very complex organic molecules. And it was at first surprising why such complex organic compounds are found in interstellar space. But now astrochemistry is explaining most of these things fairly nicely. Actually, that fact that there are large clouds of organic material in interstellar space prompted thinking among some people that the life may have originated in interstellar space and just got accreted on planet Earth. Now, I don't think this is likely to be correct, but there is plenty of organic material in the universe, and a lot of it ends on planets too. So we now know from direct observations that star formation, like Orion Nebula, famous picture of it, they're always associated with giant molecular clouds in all galaxies near us. This need not be the case with very, very first stars and galaxies of high redshift, but from most of the observed universe, this is a correct statement. And clouds are sitting there. Somehow they have to start collapsing and making stars. Usually that requires some physical cause to push them over a critical density limit. And that could be, say, density wave of spiral arm, could be a shock wave supernova, could be just a tidal force between two passing bimolecular clouds. And then once you start collapsing them, they carry on and make stars. Here's a beautiful picture of individual clouds. These are remnants of a much bigger cloud that created those bright stars behind them, which have light reflected from little dust fuzz around them and plenty of red ionized hydrogen. But these are the densest cores that they still haven't managed to evaporate. They were called Bok-Takeri globuli, and they were seen in optical pictures before any of this was really clarified. So the question then is, why do these clouds collapse in the first place and make stars? And the process of this is called core collapse, and it's intrinsic to all physical systems that are bound by gravity. In fact, would be the case for any attractive interaction. And it works like this. So you have a cloud of gas, and it's in some equilibrium. That means the thermal kinetic energy of molecules has to balance the gravitational potential energy. And this will generally be the case. It will be the highest in the middle, because that's where most of the bottom potential well. So the cloud, or star for that matter, would be in a hydrostatic equilibrium if you have exact match between thermal pressure of the material and gravitational pressure that pulls it down. All right, so I think you squeeze it a little bit. That means the core of it will get a little hotter. It will emit more radiation. If this is long wavelength radiation that can go through this material, say long wavelength infrared that can penetrate dust clouds, it will escape, thus carrying away some kinetic energy. Because now some kinetic energy has been radiated away, the cloud shrinks some more. That brings it closer again to hydrostatic equilibrium, which again leaves it with a slightly hotter core, which then shines more light and so on. And it's a runaway process. In case of stars, it stops because a new source of energy opens up in the middle, the thermonuclear reactions. Otherwise, these clouds would collapse into black holes. But at some point, you start burning hydrogen into helium that releases goodly amount of energy, and that more than compensates for the amount of energy that's been escaping from this collapsing protostar. So the core collapse leads into ignition of star in the middle, and then that's it. Then all manner of other interesting physical things happen. Interestingly enough, exact same thing happens in globular star clusters. We can think of them as a gas cloud of stars. What serves as a source of energy there are binaries, but we'll get to that later. So there's some very basic physics of star formation. So what's at play here? Obviously gravity that pulls things together. Pressure that has to balance it. But other things that can also fight gravity are magnetic fields, because they're hard to squeeze, or just bulk motions, kinetic energy in different packaging. And so if you have one of these clouds, which is sufficiently dense to collapse, it collapses according to the free fall time scale, which is if you were to drop something at the outermost shell, how long will it take to come to the middle? And because the inner shells inner to it are accelerated more, there are no shell crossings. And so all you need to do is take one test particle at the edge of your cloud, such as it is, and let it go. And the expression for that's given here, and the time it takes to do it is also given here. And so you notice that time is inversely proportional to the square root of mean density, and that kind of makes sense, because denser clouds will have stronger gravitational attraction, so will collapse faster. Okay? Now, the other concept that's important here is so-called Jeans mass. And deriving the formula is beyond the scope of this class, but this physics is simple. You have thermal pressure that balances pull of the gravity. what is the minimum mass that will push this over and make cloud collapse? And James Jeans was the first one to evaluate this, and he came up with this formula. That's called so-called Jeans mass. It's a function of two variables, temperature and density. Now, the little r inside, Rg is gas constant from PV equals RT. It's not radius. And the mu is the mean molecular mass in atomic units. So if you look at this formula, it says it's going to be proportional to temperature, 3/2 power, by that power, doesn't matter. And that, again, kind of makes sense, because if you have a hotter cloud, it will require more mass to push it over into a collapse. Contrary to that, if your cloud is denser, right, then you wouldn't need as much, and the mass will go down. So be inversely proportional to this weak power of density. So plug in the typical numbers that we observe for interstellar clouds, and assume it's molecular hydrogen. It doesn't really matter if you take a mix of carbon monoxide. And amazingly enough, it produces a value that's pretty close to the mass of our sun. Now, most stars are actually less massive than our sun. There are many more low-mass stars than high-mass stars. And so this is kind of amazing, that just if you know the temperature and the density of the protostellar clouds, characteristic mass of stars comes out. Now, stars don't come in one mass. The stellar mass function is not a delta function. And that's because the clouds are not perfectly uniform, et cetera, et cetera. So there'll be some range of densities and temperatures and magnetic fields and God knows what else. But this is a very simple application of thermodynamics and Newton's gravity in deciding how stars are made. Just as we define the mass, there is also a characteristic length